Please join me in welcoming to the podium Dr. Mark Johnson.
Thank you very much. Thank you. And are we good? Okay. Thank you. And it's great to be back here at NC State. As Mladen pointed out, I actually both have taught here at NC State and teach here, and also have got my degree from NC State, so I'm an alumnus as well. So thank you very much for having me here. The last few years I've been spending time up in the Department of Energy in Washington, D.C., working in a couple of areas. One is how we wind up driving a lot of innovation into the energy space using new advanced science and technology. And then over the past 4 or 5 years, really working on this real focused effort around advanced manufacturing and driving new technologies into the manufacturing sector to wind up growing things. Now, one of the things that I'm really glad to be here in the computer science department talking about this that really resonates a lot is, I think you guys all see the GE ads that are out there right now, pick up your grandfather's hammer sort of thing. People think about manufacturing as being this, thing of the past. Why would we do that? Why are we interested in it? We have to even just stop talking about you should go into manufacturing, because if you look at 90% of the stuff that's done right now, it's actually information technology. It's a revolution going on in bringing information technology into the manufacturing sector, driving communications, driving smart devices, driving the Internet of Things into that manufacturing sector. It's a huge value proposition out there. What's really exciting about it, by doing that, you actually drive better efficiency, better productivity, means that you can wind up actually most competitively manufacturing. So you can wind up having a stable, secure platform for growth. Another thing that's interesting, if you're at a university, universities are really interested about patents. 75% of all patents in the world, actually where they wind up getting used is in manufacturing. That's where, at the end of the day, they wind up creating value, is in the manufacturing sector. So those of you who are interested in a research job, how you wind up tying to actually manufacturing relevant problems as you define your research and development often can be the difference between having a very real thing that's the outcome versus having something that is, a nice academic experiment, but you're wondering, why would I be doing this? So connecting together between that manufacturing world and the advanced manufacturing world, and the word advanced in there is for a real reason. That is, we're using science and technology as a real competitive advantage. This is where the United States is at home field advantage. We have the best, by far, innovation system in the world. We have the greatest university system. We have the greatest national laboratory system. We're the envy of the rest of the world in terms of that. So part of my job is traveling out to people like you and saying, how do we wind up connecting so we can actually unleash that innovation ecosystem most effectively to the economy? So give you a little highlights, give you an overview of what the Advanced Manufacturing Office is, some of the work we wind up doing, get some high-level work in that area we can talk about, go through that. But I want to give you a little bit of history, first of all. When we talk about manufacturing, it really goes back to things like the Industrial Revolution. So the US Revolution actually started in 1775, Lexington Concord. Almost to the same month, you had the first incorporation of James Watt's first company. So it was the beginning of the Industrial Revolution at the same time. So you had as the background of this great experiment of democracy we're going through, the rise of the Industrial Revolution. So our founding fathers got together on this, and I'm not going to wrap this because I'm not as good as Lin-Manuel Miranda at all. However, 225 years ago next month, Alexander Hamilton was our Treasury Secretary, and he was asked to do a couple of things as a summer project, basically, by Congress. They said, first of all, should the United States issue money and go out and figure out whether we should do currency? The second question is, should the United States issue bonds? And because they had this war debt they had to take care of. And then the third question was, how do we think about this new thing called manufacturing as a country? And what do we think about this? So he delivered this report to Congress, and it's very interesting what they wound up saying is, first of all, that manufacturing is important to all parts of the United States as a result. 225 years ago, that's still true today. But it was interesting what they pointed to was not only the wealth, but it's both the independence and security of nations are actually intimately tied to the strength of manufacturing. So if you want to develop an economy, it's in the interest of that country to wind up supporting manufacturing. So it's actually in our founding DNA saying, we as a society wind up supporting manufacturing so we continue going forward. So that's the challenge we wind up looking at. So one might say, why would the Department of Energy do this? And I got my slides out of order, so I'm going to go back. Manufacturing actually sits at this really interesting intersection where you wind up saying, first of all, there's economic competitiveness out of it, right? So we can wind up manufacturing energy-related products and using energy efficiency in manufacturing. Those are two opportunities you wind up having. We have a great wealth of energy in this country, an awful lot by all of the above strategy that we've been executing on, that winds up saying, how do we wind up utilizing that to most effectively drive down the cost of the things that we wind up using every day? The second side of it is new energy technologies are an area where it's a huge emerging markets out there. Whether it's building wind turbines, whether you're looking at building electric vehicles, whether you're looking at building solar cells, whether you're redesigning the power grid, these are huge opportunities. By using science and technology in the US, we can actually drive down the cost of doing those things so we can most effectively actually manufacture those things here in the United States as well. So those are the two areas we wind up looking at. It becomes that intersection between the economy, the environment, and security. That if you wind up are successful at that, you actually have maximized energy productivity that maximizes your potential for energy growth, in GDP growth, economic growth, and also by doing that most efficiently, you actually are using your resources as efficiently as possible. And that includes even having a goal saying, how do we drive down to using all the way from solar power to drive it into our manufacturing facilities? But there is a keen alignment between these things. That's what our mission is. So that's why manufacturing is part of the Department of Energy's mission. So you wind up focusing it on a couple of things. Not only how do we wind up inventing these technologies, but making sure we can actually make them here. Focusing on three areas: energy efficiency in manufacturing, the competitive manufacturing of energy technologies, but also that combination of technology and talent. How do we tie that to people? Both you as students, and also the people as you go out into the workplace afterwards, where the people that will be working for you, how you wind up having that society out there. What you find is that actually manufacturing in advanced technology areas have the highest multiplier in terms of economic impact and also employment impact outside the manufacturing sector. You have 4 jobs outside the manufacturing sector for every 1 job in the manufacturing sector in those high advanced technology areas. In the low advanced technology, less advanced technology areas that don't require technology, it's usually about a 1-to-1 ratio. So by using your science and technology, what you wind up having is essentially a long logistics supply chain of knowledge workers behind you that wind up being supported. So it's very important for our economic growth to wind up looking at that. So how are we doing on this in deploying these technologies? So over the last decade, great increase in the deployment of wind power. It's a 3x increase. A driver behind that is that you're able to get the cost down. So we've reduced, by developing new manufacturing technologies around wind, the ability where it's at cost parity with other ways of doing it. That becomes a huge driver. Solar, same thing. 25 gigawatts come online over the last decade. Again, 20x increase. It's a 60% cost reduction in winding up doing that. A lot of that takes innovation to wind up driving that in. And the big one is batteries. So you're looking at electric vehicles out there. I think the first Model S, or the Tesla Roadster a decade ago, they made 9,999 of those vehicles, because if you make 10,000, it changes the kind of crash testing you have to go through. So we've gone to 420,000 cars, so it's a 42x increase. Huge decrease in the battery cost. That's the main cost driver behind those. Again, building things like gigafactories to wind up doing that, a huge opportunity. So if you work for the government, you get the joy of spending a lot of time writing strategic plans. So we've got a number of strategic plans that roll all the way down from the National Economic Council and the Office of Science and Technology Policy, the Department of Energy, Energy Efficiency and Renewable Energy, and then even into my office, looking at the Science and Technology Quadrennial Technology Review that says where are those areas we could wind up doing research in, to really identify those cross-cutting areas that are the most impact. 2 areas wind up coming out, and this actually aligns with what Congress asks us to do in our authorization, which is broadly applicable energy efficiency technologies. So using manufacturing energy efficiency technologies in manufacturing, so especially in what are called energy intensive and energy dependent industries, those heavy commodities that we wind up using for our everyday life. So we have a choice. We wind up saying, how do we drive down the energy to make those things or stop using them? So we drive down the energy to make it because it actually reduces the cost and winds up improving the standard of living. Also, platform materials, process, and information technologies for the clean energy manufacturing, for sustainable life cycle impacts. That is things that will have, as a result of manufacturing them, better impact on the environment. Solar cells, wind turbines, electric vehicles, a range across the things, LEDs, you name it. Huge things that wind up impacting in that area. We also look at promoting innovation partnerships, public-private partnerships between government and research groups, as well as having tools, training, and human capital development. How we wind up, frankly, wind up supporting a lot of students as a result of that. So those are some of the ways we wind up doing that work, but having it in a very directed and targeted way. So I'm going to take a little step back. The other thing we wind up doing is a lot of data gathering. Where's energy used in manufacturing and across the economy? So this is a flow chart of where energy is used in our economy on an annual basis. On the far left, so the power inputs that you wind up having. So you're looking at things like petroleum, natural gas, coal. Then you're looking at things like solar, wind, nuclear coming up in here. They're made into electricity for about a third of that, but then they wind up getting distributed down to these end uses. So you've got transportation, industrial, commercial, and residential. If you compare industrial and transportation applications on this, transportation actually is fairly, I wouldn't call it easy and straightforward, but you only have one kind of fuel essentially that dominates. So petroleum going into transportation, not very efficiently, so improving that efficiency, and wind up getting it so you can wind up most effectively using that resource in transportation so we can get around. What makes the industrial sector fascinating to work in, and is a plethora of challenges that are science challenges, is there's really no one fuel that dominates. All fuels wind up coming into that. And in fact, there's often processes where they switch between those fuels. It's also fairly efficient relative to a sector. They have a profit motive to begin with. So things that are cost effective will get deployed. The challenge is, how do you get them to the point where they're cost effective? And often that isn't, oh, I invented the thing and then I hand it over to the manufacturing people and they figure out how to make it cost effectively. What you find is once you've invented that new thing that you're going to use, I don't care if it's a solar cell, new kinds of windows, new building materials, new textile materials, you name it. What you find is when you try and go into manufacturing, that you wind up actually opening up a new science and technology challenge to solve. So if you're going to drive down that cost, it's not just inventing the thing, it's inventing the way to make that thing cost effectively. It greatly opens up that opportunity. In a university, we call that engineering, right? I mean, that's exactly what you guys wind up doing every day, is trying to figure out what's that question that you need to answer to be able to do that most effectively. So where can we wind up doing that? These are the things we use. So about a quarter of all energy from that earlier slide gets used in manufacturing. So the units here are what are called quadrillion BTUs, or 100 or 1,000 tera-BTUs is a quadrillion BTUs. You can think the US economy uses about 100 quadrillion BTUs a year, or 100,000 tera-BTUs. About 25 quads is used in manufacturing, of which about 2/3 of that goes into this limited set of energy-intensive industries. So you're looking at primary metals, steel and aluminum, petroleum refining, chemicals, pulp and paper, glass and cement, and food processing. A huge amount of energy gets used, by the way, of just drying stuff out. If you look at pulp and paper and food processing, a lot of that is just adding water, mixing, and separating water out. Also, a lot of chemical processing is that way. But these are also the industries that provide us the things that are the basis for our standard of living. So it becomes a challenge to say, how do we wind up developing a new innovative process where we can achieve the same energy service, the same product, at the same cost, but use less energy? That's what the challenge is. We also look at what we're calling energy-dependent technologies. So these are things that are new emerging technologies, things like solar cells, carbon fibers, light-emitting diodes, go down to making batteries, even things like water desalination, as we wind up moving to a world where we need to have more and more technology to ensure we have pure water. How much energy does it wind up taking to do that? All these things are achievable, but they take energy. The only reason these energy-dependent industries are not energy intensive, it's just the scale of how much they're used at this point. But so, for instance, as we start transitioning to things like using more carbon fiber technology to have lighter weight vehicles, we need to make sure that we're actually also driving out the energy intensity in making those carbon fibers. Now, as I said, there's a, and this did not copy over. This is an alignment. This is chemicals, petroleum, pulp and paper, iron and steel, and food processing, and that's a combination of all other sectors except these smaller sectors down here. But this combines what's the on-site energy consumption, that is how much energy is used in manufacturing those products in that sector, and then what's the related emissions on it. This average line is basically the industry, or the average of energy versus CO2 emissions across the entire economy. And you can see that things like chemicals and petroleum refining, improving efficiency in those areas are a key challenge. Now what I'm going to get to on this, and this will tie into what you all are doing, is how do you wind up improving it where you have a large factory with $1 billion in capital infrastructure that you wind up having, you're not going to tear it down and rebuild it completely, but we need to drive out energy efficiency out of it, make it as efficient as possible. Often the way you can wind up doing that is things like better computational models, so you can actually operate those systems more effectively. Coupling in sensors, controls, new control algorithms that you can wind up using and testing out. Better real-time data analytics, better decision making. A chemical plant will have things like different feedstocks coming in on a daily basis, slightly different impurities in it. Having sensors that can wind up adapting to that, so that then you can deliver a continuous stream on the outside. What that's done is it's actually transitioned these problems from being problems of physical science-based technology to also being information technology problems, to be able to accomplish it. That's the huge breakthrough that we have. Once you've converted any manufacturing problem from being a physical science problem to something that's an information technology problem, the pace of innovation starts moving at Moore's law. Often innovation is slow in these industries historically. This is the big lever that you all have the opportunity to use at this point to wind up moving into this area and really having impact as a result of it. So you've got economic impact, environmental impact, energy impact as a result of it. We also look at some things, these big, remember, chemicals and petroleum are the biggest energy intensive industries. We go out and we wind up gathering up information every 4 years of where's energy used in each of those and how low could you get the energy coming out of it. So the chemicals industry is an interesting one. This is, the total size is, again, about 3.5 quads of energy gets used. If you were to wind up replacing every chemical factory with a factory that is currently deployed for that product, whether it's ethylene or ammonia or something else that you wind up making, that is the most efficient factory in the world that's economically deployed. Because these things have 50-year life cycles when they build the factories, technology gets developed. If you were to replace them, you'd move that from that point down to this point. So that's an adoption opportunity on it. If you were to go through and look at the scientific literature and say people have developed catalysts, they've developed new reaction technologies, new process technologies for separating, things like that. But it's not yet mature where it's cost effective. This is literally looking at the scientific literature and seeing someone, over in my department, material sciences, come out of their electron microscope and said, oh, I have a little, here's my little sample, it works. You need to use it at a full factory scale, right? But if you were to wind up maturing that technology, that would move you to that point. That would drop the national energy budget by 2%, just doing those changes, right? But this is the R&D opportunity to wind up making those things cost effective. So how do we wind up identifying all those challenges? Now the last thing is if you were to take every chemical reaction of the entire chemical sector across industry, and you say, what's the Gibbs free energy? It's called the exergy out of that, and take advantage of it. The chemicals industry is negative. They are net exothermic as an industry. They should be providing energy to the economy, not consuming energy in the economy. So that's your thermodynamic limit. So there's actually room for innovation in these spaces that we haven't done, whether it's scientific research, whether it's manufacturing research, or it's adoption of the technologies. And we've done that for other things like pulp and paper, and then you're looking at iron and steel manufacturing as well. But we have tremendous potential to innovate in these areas. We also go through and look at where's energy used. About 7 quads of energy used in process heating. So how is that? The vast majority of that is direct heating of things like using natural gas in heating up things like, distillation towers. Just like your house, natural gas, to use the exact heat value directly, is the most efficient way with current technologies to do that. But if you wanted to reduce that further, and let's say you want to do that, we're using solar energy to electricity, what you need to figure out how to do is how do you reliably connect the entire energy infrastructure, the electrical infrastructure, with high renewable penetration into the manufacturing sector. That's a huge challenge for things like microgrids, energy storage, all the power electronics stuff that's done research around here at NC State. That's the opportunity you can wind up getting to, though, is you've got a way to wind up actually affecting that. And again, doing that on a cost-effective basis where we can get the products at the end of the day that we want. We kind of get that triple bottom line as a result of it. This is the Department of Energy, by the way. So for folks that want to know how we're organized, that's my boss's boss, Secretary Moniz. This is David Friedman, the Assistant Secretary for Energy Efficiency, or that's actually Lynn Orr, the Undersecretary for Science and Technology. Dave Friedman, who's the head of EERE, and then I'm in the Advanced Manufacturing Office within that. This is the science and technology part of DOE. We run the national laboratory system of the United States, so 19 national laboratories across the country. We end up supporting research at universities. We end up supporting research at companies. We support partnerships between companies and nonprofits and states. We end up getting that technology out there, so doing the basic research and the applied research. Other parts of DOE are the Nuclear Non-Proliferation Security Agency. So the history of DOE started with the Manhattan Project. It's the carryover of that, how we wind up having our nuclear stockpile and manage that well. And then the environmental security and legacy management, which is a nice way to say, how do we wind up cleaning up after the Cold War? Because there's still things that are needing to be cleaned up on that. So huge amount of effort that goes into those areas. If you look at the technology areas we wind up working in, we've wound up looking at it in 14 different sectors. And as I said before, it's looking at things that are efficiency technologies and enabling platform technologies. I'm going to dig into some examples here to show you guys in a few minutes. 14 areas. You can look at things like critical materials. These are the rare earth minerals that, frankly, there's 97% market share of the global rare earth minerals are coming out of China. Why you need a rare earth mineral is because they make strong magnets. Why do you need strong magnets? Because that's what couples electricity to force. So if you want to make motors, if you want to make actuators, you want to make robots, you want to make things that actuate, you need strong magnets. Having that as a critical challenge out there that's a monopolistic challenge is an issue, and how do we wind up developing technology alternatives around that? We've got things like magnetocaloric cooling materials, wide bandgap power electronics, development of materials for harsh surface conditions and corrosion-resistant environments. Corrosion across this country, if you look at all the infrastructure, it's a $1 trillion a year, with a T, $1 trillion a year cost. We can figure out how to wind up minimizing that by understanding the materials so we can actually manufacture them more effectively. It's also the limiting factor for things like power generation, is how hot you can make something without it falling apart. Jet aircraft engine, same thing, before you wind up having those materials come apart. So understanding those materials, developing advanced materials overall. Additive manufacturing, I'm going to get into this because we do a lot of work in 3D printing technology. But 3D printing like you've never seen before in terms of how you use it for building large-scale structures that you'd actually wind up using in a produced area. Composites, roll-to-roll manufacturing, process technology, process heating, advanced sensors and controls. This is the information technology side of stuff that you all are working in. Waste heat recovery, combined heat and power, and then sustainability in manufacturing. How do we wind up using those materials more efficiently? This is traced down the same set into those two categories, energy efficiency technologies and platform materials and process technologies. Now what's neat about it is if you wind up plotting that back to those industry sectors that I pointed out, every one of those industry sectors winds up getting affected by information technology, process technology, combined heat and power and grid integration, and sustainable manufacturing. We work with those industry sectors and we work with, let's say, their industry trade associations, and they'll pull together companies and they'll say, where do you need R&D done? And they prioritize where the R&D, that's the long-term research that would be done. Turns out every one of those industries prioritizes sensors and controls as the number one thing they want to have done. So instead of funding some given sector and picking how you wind up allocating your budget between sectors, what we wind up doing is saying, let's identify this as a technology problem, let's invest in the technology solutions and move forward in that way, because that's actually where we have our sort of home turf advantage, where we can actually wind up having that leverage between industry sectors, and we wind up moving forward in a competitive basis. We do this through a number of ways. We have what are called technical assistance programs, research and development consortia, and research and development projects. I'm going to click through the technical assistance programs real quick. Things like our Better Plants programs. This is getting corporate commitments to energy efficiency and voluntary reporting on progress towards it. By doing that, it does what's called getting energy efficiency in the boardroom. So you wind up having, once you've made those corporate commitments, and most corporations right now, to do things like customer acquisition and employee acquisition, are making real commitments and public commitments to energy efficiency and sustainability. But tracking their progress towards it, what that does is it winds up making it a corporate value. And we're not telling them that often when they wind up implementing this, they actually can make more money by doing that. It's saved billions of dollars in the energy costs as a result of that for US companies. We wind up working with them to give them national recognition, some in-plant training, connecting back to technical resources they can wind up leveraging. We also have things like ISO standards, so standards for how you actually monitor energy efficiency. Huge breakthroughs about 25 years ago where the US was running into challenges around the quality movement. I think some of the folks down here in the front remember that when they were, Dennis, I think you were right in one of the forefront of things like ISO 9000. What the key thing it wound up doing was it tracked how do you measure quality? How do you develop a standard for that? We can do the same thing for how you measure energy across manufacturing. And it's having that process so you've got a level playing field between them. And then how do you wind up validating and verifying that? We also work on things like combined heat and power, providing technical assistance on that. That means going in and doing some engineering analysis for folks, whether these will wind up paying off. And in fact, here at NC State, they wind up having the Combined Heat and Power Technical Assistance Center for the Southeast United States. It's actually based here at NC State. And then the final effort is looking at their Technical Assistance Industrial Assessment Centers. Again, NC State has one of the industrial assessment centers that works with small, medium-sized manufacturers doing energy efficiency audits for them. Students, some of your colleague students over in industrial engineering actually wind up learning hands-on how do you wind up doing energy efficiency and energy management and manufacturing as a result of that. Small businesses then wind up seeing where they can save energy. Key thing, we're not actually implementing it. What we're doing is doing the analysis, giving it to the company. Now, 30% of the recommendations are adopted within the first 12 months. That pays back about 4 times the federal investment in 12 months into that area, into small businesses. Over the last 40 years, we have almost 18,000 small businesses across the United States that have taken advantage of this service, with over 120,000 individual assessments. So we're actually producing the students. We're also getting savings in small businesses. Research and development projects. So we look at individual problems from everything from how you wind up developing a laser drilling process so you can actually make very, very, very small holes. Why do you need to make very, very, very small holes? So things like direct fuel injection in diesel engines. So you can get more efficiency in those. How do you wind up doing things like using that in some battery technologies as well so you can interconnect layers on it, things like that. New membrane technologies you can wind up using and developing membranes that align a lot with some of the things that are done in the non-woven center. New lightweight metals that you can use for more energy efficiency, so you can use things like magnesium inside of and aluminum more in vehicles. And then things like new battery technologies, so a solid state battery electrolyte. How do you wind up manufacturing that on a cost-effective basis? We look at things like having high efficiency distributed energy devices, so things like small compact gas turbines that you can wind up using on a distributed basis, or very efficient high combined cycle diesel systems. So out of somewhere like Cummins that they use in the industrial sector for distributed generation. We also work on things like next generation electric machines. So how do you develop new alloys that you can use for magnets, soft magnetic and hard magnetic materials? how you wind up using the advanced semiconductors that are coming out of places like the Freedom Center and out of Power America in new high-speed motors. How do you wind up developing the technologies to wind up doing that sort of work? And then how do you wind up developing superconductors so you can actually make wind turbines out of superconductors on a cost-effective basis? So we've got a portfolio that winds up working in that area. Then we go into additive manufacturing. And so one of the things we recognized in our national labs is how do we wind up sort of crossing the boundary? So national labs are wonderful gems, but how do we cross the boundary so we can bring more students in, but also bring more companies in? Because they can kind of be off-putting places. So we ran this experiment out in Tennessee where we established a building that's outside the national lab, it's over towards Knoxville, and said, let's make it where companies can come together and they do work. They're going to focus on a couple limited set of things, and we've focused on things like additive manufacturing, so 3D printing technologies, and looked at things like carbon fiber technologies as well there. Now with the additive, what's neat about it is the manufacturing demonstration facility, they're tied to the national lab. So if they need to make use of things like the supercomputing facilities, or they need to use things like the spallation neutron source, the big science facilities, they're big nuclear accelerators, that sort of stuff, they have access to it. But you can also bring things like the head of additive manufacturing for Boeing and the head of additive manufacturing for Ford both have offices in that building. So they're working together with the scientists and really saying, here's where the common challenges are. A couple of things they worked on. One is for making metals. So you may see that there are things like jet aircraft engine parts now there that are being used in that. So they teamed up with, a key element is the people that make the equipment in this. So this is a company called Arcam out of Sweden. So you'd say, why would we care about a company out of Sweden? Well, there are more employees in Arcam in West Knoxville, Tennessee now than anywhere else in the country. Second is, Arcam is actually paying to use the national lab as a result of it. Third thing, by developing technology together, and this is to be able to do metal additive manufacturing, they've actually wound up developing and advancing their technologies to the point where this company was actually just acquired last month by GE for $650 million. So think about that, a 50-person company doing a hard science technology by working together is now a US-based company, and we now have a metal additive manufacturing equipment base here in the United States. So it's reshoring that manufacturing. Then the last thing, and this is what I find fascinating, is anyone in here a material scientist? Come on, tell me there's one. Okay, a couple material scientists in the back. This is not a image, this is what's called a neutron tomography image of a high performance alloy. It's Inconel 718 used for high temperature. What they're able to do is by doing computational modeling of how you put the heat into the part while you're doing 3D printing, they're actually able to orient the grain structure and design where the grains are oriented inside the material. So this isn't like polished and looking at the surface of it here. This is actually neutron tomography of the orientation of the grains inside the material. You're actually not able to just design the outside surfaces of these parts. You're able to design the inside surface of the parts. It does two things. One is it gives you a great design tool you can wind up using and leverage that you can wind up all those things like how you control the existence of harsh surface conditions and stuff like that. But more importantly, if your design tool requires you to map every inside part of it, suddenly the computational complexity of being able to do that challenges the most complex genome sequencing kind of problems, actually genome phenotype sequencing matching problems that the computer science world is looking at right now. These are some of the hardest mathematical problems in the world to chase down. So really cool stuff, but it's also really interesting science. The other thing we did was we looked at saying, can we wind up making big parts? So we wound up teaming up with a company called Cincinnati out of Cincinnati, Ohio, longtime machine tool company, and they wanted to get into 3D printing. So they had this robotic system and we added a 3D printing head to it right here. And this head was designed to print 20 pounds of material an hour. How many people have done like MakerBot and 3D system, right? So that typically prints, that size of material in like 5 hours or overnight, something like that. This thing will print 20 pounds of material in an hour. That was the original design scope. The latest design's almost a ton of material an hour it winds up printing. So we wound up printing, you can see in here, building out cars as a result of it. So this was a year and a half ago, or 2 years ago, that we wound up developing the printer, then teamed up with a company called Local Motors. They wound up printing the world's first 3D printed electric vehicle car, and that could drive around, you know, it was, I think, top speed of about 30 miles an hour. So that was September of 2014. We actually, the first car that drove around, we actually didn't print it in a laboratory. We printed it at a trade show where they were showing this piece of equipment. So now Cincinnati's in the business. They're selling these things like hotcakes. Companies that developed the materials to work with them that were doing research developed the polymer carbon fiber blend material. Then you wind up having Local Motors. They're a startup company. They've started building micro factories that they can design and print cars. But if you look up close to this car, it kind of looks like a layered structure across that. So you want to clean it up. So True Design developed a surface finish process. And in 6 weeks, they went from having that car to having that car. So how many people are car people? I am. This is actually the equivalent. It's an electric vehicle version of the 65 Cobra that was the first car that the United States and Ford and Cobra beat Ferrari in the Formula One races. What's neat about this, and also, and this is a side story, is the safety guy at the National Lab would come in every night when they were doing this project and start taking pictures. And for those of you that are physical science-based people, having your safety guy take pictures every night is a little nerve-wracking. And after a couple of nights, finally asked him what are you up to. He said, oh, I'm sending pictures to my brother-in-law. He's really into these cars. So, okay, great. A couple days later, he's taking more pictures. Like, your brother-in-law's really into it. Said, well, yeah, back in '65, he drove for Shelby and won the Manufacturers' Cup. So a guy named Bob Bondurant, who runs Bondurant Racing out of Phoenix still, he's in his 90s, so he's actually taken this car out. And I say, for a 90-year-old guy, that guy can still drive. So he was, yeah, and the top end on the thing is reported to only be about 90 miles an hour. So, and also the governor of Tennessee, it's a street legal, he got it at a license plate. So, so that was kind of fun to wind up doing. We then said, can you wind up actually going bigger? So got together with some designers and said, hey, can you actually print a house? So GE actually has appliances inside there. There's a bed. There's a whole house inside of that. All the external surface of this is 3D printed. It's high efficiency on it. So testing out new technologies. Actually has vehicle-to-grid connection. So the natural gas vehicle here actually powers the house. Then we said, can you actually take 3D printing and use that for making manufacturing of wind turbine blades? So we started talking to the wind turbine blade people. They said, don't manufacture the blade, make the molds that you make the blades out of. That actually solves a real problem we have, which is tooling is the longest lead time item they wind up having. It took them 2 days only to print this tooling, go from design to having it printed out on a 17-meter blade. It also opens up the design envelope so they actually can make more efficient wind turbine blades by doing that at lower cost. You can see these little channels down here. That actually changes the heating that they use when they're putting the blades in that wind mold. Now, especially when you get out to the Midwest, some of the wind turbine blades are getting so big you can't even ship them anymore, 90-meter blades. So you want to go on site. This material is actually recyclable. So what you can do is take the printer out into the field, print the molds, make the blades, put the blades up, throw the whole thing into a wood chipper, go somewhere else, and start over again. So a completely recyclable, low-footprint, on-site manufacturing as a result of it. All because we started looking at saying, hey, can we print at high speed? Tremendous science and technology that comes out of it. We're looking at how you can accelerate the speed at which you wind up developing new materials as well. So for the computer scientists here, anyone in computer science working in material science right now at all? Or any physical science? You should be. Because it takes 20 years to go from design, and I know at least one person is an NC State alum who's actually working on this problem in a startup company. You go from design to implementation of a new materials technology, it takes about 20 years. Often that is, how do you wind up dealing with the data? And the streams of data that are coming in both on your experimental data, real time and over time. So if you can wind up taking all the data of all the materials research out there and making sense of it quicker, it's the same problem that you wind up having in every other field. People are drowning in data. You can actually accelerate the time from discovery to adoption. That has a huge economic impact. I'll give you an example on it. Your colleagues that do materials development will use these big giant light sources. They're called synchrotrons, do X-ray analysis on them. Here's how it typically winds up working. Your advisor puts in a proposal. They get about 2 weeks of time on one of those synchrotron light sources to go in and do your experiments. The students go up there, they work 24/7, they take all the data. They come back, they start doing the analysis, And a month later they say, oh, we were close, but we didn't quite do the right experiment. We need to have done the experiment better. I wish we could wind up analyzing that data real time. So if instead you wind up treating this as a data science and an analytics problem, where you're actually doing the analysis of that data on the fly while it's being taken in, you actually can improve your research productivity. So if you can minimize the amount of time so that the physical science researchers don't have to go back and run another experiment, you think about that as a productivity improvement. DOE has about $10 billion worth of scientific assets out there. If you wind up improving the productivity 1% a year, that's a $100 million business opportunity right there. That's just a data science problem. It's just a data science problem. But it's an algorithm, right? You can wind up doing that in a lot of these physical science areas, and you can wind up accelerating the time it takes to go from discovery and the need for things like a new material for a new energy system and having that solution available. So it has multiple impacts, winds up happening as a result. We also, as the Department of Energy, manage our national security high-performance computing assets, things like the Titan computers, supercomputers, that the national labs have. So I think there's 5 of the 15 most powerful computers on the planet are run by the Department of Energy. How do we, instead of using those just for scientific research and using them just for national security research, how do we wind up applying them to new applications out there? So our colleagues in the department in the transportation area wound up doing that for modeling here of airflow, CFD modeling around trucks, and those little skirts that wind up coming in. Those things wind up along the edges of trucks. They save 1 or 2% of the fuel efficiency on a car, on a long-haul truck, just by putting in $50 of metal on either side of it. All came out of computational modeling. You can apply that to steel making. You can apply it to combustion in a jet engine. You can apply it into pulp and paper making. Really interesting science and technology problems where you go all the way from molecular dynamics simulation up to an entire factory. How do you wind up connecting that together? And in fact, we're doing that with Purdue. This is Dr. Chen at Purdue in her visualization lab as well, but using the computers at Livermore in modeling blast furnace. This is, I think it's the US Steel blast furnace in Gary, Indiana. That's the largest individual CO2 emitter in the United States. You're able to actually, just by doing that modeling and from what they have from that modeling, able to improve the productivity by a couple % in those units. In a commodity business, a couple of % is the difference between being profitable and not being profitable. Plus, it winds up reducing the use of energy and the emissions that are related to that out of those facilities. Huge, huge impact that can happen. Then the last thing we're saying with our national labs in terms of projects is we say, how do we wind up using them better as a way to work with small businesses? The model for both universities and national labs is we develop technology, we spin it out. You hear that, spin out all the time. Can we reverse that? Can we spin it in? We have innovators, particularly student innovators, in physical science areas that are interested in working on energy problems that really, once they graduate from the university, there's nowhere to go. But they're innovators all over the country. Can we wind up using the national labs for a couple of years? Also, they're not ready yet to start a company, right? They've got a science idea, but they don't yet have a company they can raise. So how do you wind up coming into a national lab, wind up providing support for people first couple of years, that basically it's giving them a postdoc in the national lab environment so that they can work on their business plan, wind up surrounding them with mentors and business experts so they can wind up, and it's not the national lab people, it's bringing people from the outside in, so that then, by the time they're done, they're able to actually wind up getting a successful company that comes out. So we tested this out at Berkeley with a group called Cyclotron Road. Started this about 2 years ago. The first 5 teams that wound up coming in have over $10 million of follow-on funding, and every one of those teams has at least 18 months of runway at the time they wind up exiting out of the program. We're testing that out now at Argonne National Lab in Chicago and at Oak Ridge National Labs out in Oak Ridge as well. And the question is then, I mean, we can work with the national labs on this. There's no reason we can't work with a place like NC State as well and say, how do we wind up creating it where wherever the science and technology is developed, you come into the university, you can leverage all that capability, you wind up accessing the students, the capabilities, the knowledge out of the business school, you wind up getting mentorship and training, so that then you wind up, when you wind up leaving, you're actually more effective. Why this is important for energy? There was a huge peak in clean tech investment and venture capital around 2009, 2010, that's tailed off. The third quarter of last year, there were 0 startup venture capital deals in the United States in clean energy. 0. What we find when we look at that is it's such a long lead time in these physical science-based science and technology problems for energy that usually the projects are just too early at that point. So by embedding them in things like universities and laboratories, you actually give them a time to mature to the point where they're actually sponsorable. So that's the gap we're trying to address in this. Then the last thing we wind up doing, and I'm going to hustle through this, are some of the consortia we work on. So consortia are where you wind up getting more than one company working together on things of common interest. Now, why do you need that? Well, Henry Ford owned everything from steel mills and iron mines all the way to dealerships. So in terms of economics, when they did research and development, they could wind up appropriating the value of that innovation across the company, even if it was an innovation that required part of the iron mine and part of the end dealership to work together. We don't live in that world anymore. You've got specialization where you've got things like an auto company up here as an OEM working with their tier 1, tier 2, tier 3, and even material suppliers below that. So no one firm winds up getting advantage out of it. We find this in a number of areas. Power semiconductors is a great example of that, where you say, we need to have that innovation. Someone's invented something, but we need to mature the manufacturing technology. How do we end up building an environment where universities, national labs, companies can all come together and work on these shared challenges? And as a result, do it in what's called a pre-competitive basis. And then once they get to the point where they're competitive, they all go to their neutral corners, but it's finding that common ground. This is we can go through that. This is what we wound up doing. We've established a series of these manufacturing innovation institutes here in the United States. It's called Manufacturing USA over the past 3 years. Power America is here in North Carolina at NC State. Actually, Nick Justice is the director of that. We have a Composites Institute. We have a Smart Manufacturing Institute for real-time process control that NC State's a part of as well. We also have 2 that are currently in what are called merit review. They're technical merit reviewed for chemical processing and sustainable manufacturing as well. Our colleagues in the Department of Defense have stood them up around advanced fibers and textiles, photonics, additive manufacturing, lightweight metals, digital manufacturing, and flexible electronics. So these are looking at that advanced next generation of technologies. So here at Power America, the goal is you need to have these wide bandgap semiconductors for things like industrial motors, consumer data centers more efficiently, solar and wind integration, things across the grid. When it was launched in 2015, you've got 17 industry members working together with 7 universities, 3 national labs, all working together on it to wind up driving down the cost of these wide bandgap semiconductors. One of the key elements that wound up happening is out here in West Texas, there was a facility that used to be used by Texas Instruments that they were ready to close. It was not doing silicon carbide, it was using silicon to make things like calculators. And as that market moved on, they didn't know what to do with it. Well, they worked to wind up developing this group called XFAB to wind up doing silicon carbide-based manufacturing as what's called a foundry business there. So you can come with your designs to XFAB for the next generation chip, and they'll wind up actually manufacturing that out of silicon carbide for you. We've done the same thing with advanced composites. Now the reason for advanced composites are we have those composites like carbon fiber and things like the 787, but if we're going to wind up using them in automobiles for lightweighting, we need to reduce the cost by at least half. We need to use about a quarter of the energy for it, but also increase the recyclability of it and speed up the pace as well. They build 1 787 a day. A small production line for a vehicle or in the automotive sector is 1 part every 6 minutes. So you need to have new manufacturing technologies to be able to do it at that high speed. It's new materials and new processes. Wound up having Tennessee, Indiana, Ohio, Michigan, and Colorado all working together to wind up developing that for that range of technologies. Smart manufacturing really is focusing at real-time process control. As I said before, getting that Internet of Things into the manufacturing sector, but how do we do that securely, reliably, and robustly? And then the last 2 are looking at this advanced chemical processes and looking at recycling and reutilization of materials. We wind up addressing critical materials in a similar consortia, where we've got a rare earth research center based out in Iowa. It winds up working with 4 other national laboratories and about 6 universities. It's interesting, since we've stood this up, the global demand for, and frankly, rare earth minerals, first of all, for those of you who remember your chemistry, the 2 little rows at the bottom of the periodic table that are offset, it's the upper of those 2 rows. This is a natural monopoly. We can go into why it's a natural monopoly as far as that, but basically you need to develop separation process technology or develop alternatives. The transition to light-emitting diodes and the phosphorus used in light-emitting diodes has actually reduced the global demand for one of those elements, terbium, to almost nil over the last 3 years, where we were looking at a global crisis over this because of quotas coming into the United States out of China. And so developing that technology as technology alternatives. These are key for energy efficiency, but these lights don't use terbium as a result. Same thing for magnets. How do we wind up utilizing and minimizing the amount of rare earth in magnets? The last challenge I want to talk about is one in water. And water's an interesting one where you look at it, and you've got droughts that are increasing out there. If you were to wind up using current technology for desalination, so reverse osmosis desalination, to provide the water across the country, you can actually provide clean water using energy. However, you'd start using as much energy as used in the entire steel industry just to have clean drinking water. So the challenge is, and also, by the way, the cost of your water would go up by a factor of 4, and you'd wind up saying you'd use about twice as much, 2 or 3 times more energy than we use today, emitting related CO2 and meeting what those qualities are. And this isn't just a problem in coastal regions where you say, oh, that's California, who cares, right? Well, it turns out you go down to eastern North Carolina, you're getting brackish water intrusion into the freshwater lens because we're drawing water out of those barrier islands, out of the aquifers. How do we wind up filtering that water more effectively? You go to the Midwest, you've got places like Toledo and Cleveland, where they're actually having to shut down and having boiled water alerts in the summertime because you wind up having more and more things like algae that are poisonous algae, the cytotoxins in the algae in the water. But just treat these things as scientific challenges and say, okay, how do we wind up dealing with that wastewater, dealing with that produced water, dealing with brackish water, and just figure out what are the new science and technology we can work in that area. So we wind up looking at that and saying, here's where the goal is, and we just say, what's the technological pathway to get down to 50 cents a cubic meter, 50 cents a metric ton for clean water? And it's possible to do that, but it needs science and technology solutions. So that's what we're looking at as a clean water area, saying how do we wind up using these different sources of water, using different energy inputs, whether it's waste heat or electricity or heat and pressure, wind up having it where our goals are just to have pipe parity, and then you wind up having that high quality. This brings together a number of technical challenges, but basically bringing data science, bringing biological science, bringing material science, bringing industrial management all together to work on these challenges to address it. Bringing textiles in, so membranes, huge, huge issues. So, in summary, we've talked a little bit about how energy is important across the entire economy, that it's a foundation of our economic prosperity and our economic competitiveness. Technical innovation in this country is what can enable improved economic and energy benefit across there. But how do we wind up leveraging these advances we have is really the challenge we work on. So with that, I'd be happy to say, what does success look like as we're not just inventing energy products here, but we're actually competitively making them here. So with that, thank you very much. Be happy to answer questions.
If you have a question, if you'll raise your hand, I think we have time for we'll take 3 questions.
And I'll be around for a while.
If we have more than that, we're having a little reception and folks can take them out there. So raise your hand and we'll have somebody bring you the microphone because we want to capture it for the video.
Hi, you said that, or you talked about additive manufacturing, and I've heard from a lot of places that it has the potential to replace like traditional manufacturing processes. Yeah. Is that at a point where it's as energy efficient as those traditional processes?
Yeah.
And if not, how long until it would be at that point?
Yeah, actually we've done a study on the energy efficiency of the 3D printing itself. And you look at some part, it depends on the part, first of all, you look at. So you take especially something like titanium. That's why additive manufacturing is important for titanium. You look at things like, you go on an airplane, the little brackets that are underneath seats that hold you up, they're titanium because they have very high strength to weight ratio. Titanium takes a lot of energy to wind up actually producing that titanium. So the embodied energy is in it. And they have a thing called the buy-to-fly ratio on there. So to answer your question in the short, it all depends, and we've measured it. In some parts, yes, other parts not. The buy-to-fly ratio is a key thing because the way you make those parts right now, you buy a big block of titanium and you basically bring in a machine tool and you cut away 99% of it. They'll have a buy-to-fly ratio of 100 to 1 in some of these parts. All the energy it took to make that titanium that wound up turning into chips that you're actually just going back to recycle to make more titanium out of and put more energy in is all lost embodied energy. So that's actually where one of the big wins is in that area. Now, additive, I think, and this is why we're looking at the tooling. I gave you one example in that area. Another area you wind up getting a speed is actually, advantage in this isn't just the energy efficiency, but the time to market, and it's not making the part itself, it's making the molds. So you look at something like the metal casting industry. The time it takes to get tooling done in that is 16 weeks. So if you're going to wind up having a part cast, it's going to take you 16 weeks, and you're a designer, often what people have been doing is they just wind up shipping that offshore. If instead you say, I can make the tooling, and this is the way you make the mold, in 24 hours, and then I put that into a sand cast and I wind up molding it, and I can go from saying, I'm here in the research triangle, I'm a designer, I've just designed a part that I need made, and I can get it, I have a way of getting it shipped in 72 hours to me from a metal casting company in Youngstown, Ohio, versus having it take me half a year. It completely changes the dynamic how you wind up working in that area. In doing that, that also gives you a third option. It gives you the ability to have a much wider range of technology designs and part designs. So you look at companies like AutoCAD or Dassault Systems, how you wind up using that sort of genetic design rules so you can actually design a part. So in the life cycle of the operation, you know, those supports that are underneath you in a plane, how do you make the least amount of weight in those so that then it takes less fuel to haul that part around? So what you asked is actually a really hard question. The life cycle energy impact is a longer impact. We've done the thing where you put an amp clamp on the thing and you measure how much material it takes relative. Your buy-to-fly ratios typically in a 3D printed part can be, you know, in terms of the powder is sort of 1.5 to 1, something like that. So it's a much lower buy-to-fly ratio, but that's where that is on that. So did I answer it? Or, okay. But it's an active research area as well. Sorry, I didn't shut off my phone. It's ringing up.
One more question. Thank you very
That's fine. Thank you very much. Thank you.
Thank you so much.